Great. And I can try to keep it to 15 minutes so that we have more time for discussion. Thanks for that introduction, and it's a pleasure to be here presenting, especially with Nadesh, because our technologies complement each other. So it's quite nice that we're here together. And I think it will be good for the audience as well to see us presenting together, because then you'll understand how our technologies are different and fitting into different contexts and complementing each other, actually. And so I'm based in Sweden, where I did my PhD developing a technology to convert urine into a dried fertilizer. And then we started a spin-off company called Sanitation 360, where we're working to commercialize this technology. And we're part of a few different projects where we're working on how to implement, how to scale up, and how to get over some of the barriers for those processes that I'll discuss later. And from what I understand, the background of the audience, you already understand the importance of nutrient recycling. So I dive quite quickly into just the concepts and what we are working with, but definitely if you have questions as to the importance, we can definitely discuss that later on as well. So briefly, Sanitation 360, what we're doing is we're converting waste urine into a valuable product. So why urine? I thought this would be interesting for you just to understand why we focus on urine and not feces together or at all for our company at the moment. So on this graph, you have the percentage, and then you have the macronutrients, nitrogen, phosphorus, potassium, sulfur, and then the total mass. Then urine is yellow, feces is brown, gray is the rest of the water. So you can see that the urine constitutes the majority of the nutrients that we find in our wastewater, yet it makes up just a very small fraction of our wastewater. So we produce about a liter and a half of urine every single day, and then we produce on top of that, the amount of wastewater is maybe 150 liters, depending on your household and where you're living. And within that urine, we have enough nutrients to produce 500 grams of wheat. So there's enough nitrogen, phosphorus, potassium to grow 500 grams of wheat, which is enough to produce a loaf of bread. So what that means is that every single day, each individual is throwing away a loaf of bread. So you can multiply that by your household, by your city, by the world. By not actually managing these resources in a circular fashion, we are just throwing away that much bread every day. And there's loads of research showing that urine is a good fertilizer. So the question is, why aren't we using it? And there's a few barriers. Often people think a barrier in terms of acceptance, but we see through the surveys that we do that there's quite a high level of acceptance. We think that farmers might not accept it, but the concept of urine as a fertilizer is quite acceptable. It has to do with the form that it is in for the farmers to be able to accept it. And what is limiting large scale up for us is logistics. And how do we get the urine from the urban areas back to the fields in an effective and economical way? So it becomes down to a matter of costs as well. So if you can think of all of us producing this amount of urine every single day, then for a city of 1 million people, you have 1.5 million liters of urine being produced every single day. And we only use fertilizer once or twice, maybe 3 times a growing season. And in the Nordic countries, we only use the fertilizer a few times a year because we have such a shorter growing season. So what do we do with that large volumes of urine during the rest of the time? And we can't simply just evaporate the urine because then we lose the ammonia to the atmosphere in our technology. So I'll explain a little bit about how it works. So when we go to the bathroom, the main form of nitrogen then is urea. And urea is the most commonly used fertilizer in the world. This urea is quickly changed to ammonia, which is volatile. And this is because of urease enzymes that are found in the toilet bowl, pipes, storage tanks. They're on our fingers, they're in the soil. Bacteria use them to regulate their environment and as an energy source. And so in Nadesh's technology that you'll learn about afterwards, they want this process, they want the nitrogen in the form of ammonia, and she'll explain how they're able to concentrate it and use it in that form. In our process, we actually want to stop this process and keep it in the form of urea and then remove the water. So that's the fundamental difference between our technologies. And so for us, we do a chemical treatment. So we stabilize the urine by altering the pH to either less than 3 or above 10. And this blocks the urease enzyme. And then we're able to just evaporate the water, because urine is still 95 to 97% water. So we need, in order to make it effective to store, transport, and apply it as a fertilizer, we need to remove that water to make it more economically viable. So first, how do we get the urine? You already had a presentation previously as to the different types of toilets, so I'll just share the partnerships that we have and not go into too much detail. Right now, we work with portable toilets. So this is a local group in Sweden where they have urinals that get sent out to different events. And we put our chemical stabilizer inside. They distribute the urinals. And then I drive around with a pump truck and suck up the urine and take it back for processing. And we also work with this Löfven toilet, which is a new urine diverting toilet. So instead of the traditional hole here, it's using surface tension so that the urine is captured using the teacup effect. Typically, it slows down the speed here, so then it can follow the curvature of the ceramic, collect the urine separately. This is an installation that we have in southern Sweden, where we have this urine diverting flush toilet. And so the urine is collected directly underneath, where it comes into contact with our stabilizer. And then it is, we apply heat through electric heat pads on the bottom. And then we use the ventilation from the bathroom to do the drying. So there's an intake, and then the air passes through and then up into the building's ventilation. So this is a concept that we have as a retrofit. So there used to be a regular flush toilet, and then we retrofitted to this system, and it's on display at one of the main utilities in southern Sweden as an example of how it can work. Within this Rewise project, we are also putting in a multi-story building concept where we will have the same Löfven toilets and then our system in the basement. And with this, it's designed that instead of having people needing to come into the individual bathrooms to maintain it, so it slides out and you collect it that way. Here, it can be more automized, and then I just have to come twice a year in order to empty it. So how does this all work? So I don't care how the urine is collected as long as it is clean and that I can put my stabilizer in correctly. So we're always looking for different opportunities in order to increase the amount of urine that we can collect. From there, it goes into a concentrator. So this can be on site. We also have a portable system where I can collect the urine and then have the system within a trailer so that it can be more of a localized on-site treatment process. So on-site, we concentrate to a liquid, and then we have a final processing phase to get it into a dried pellet. And then these dried pellets can then be used with conventional farming equipment. And I'll give a little bit of details as to how fertilizer is performing. So we're able to go from 0.6% nitrogen to 15% nitrogen. It's a concentration factor of 25. And what this means is for barley, we want to fertilize 85 kilograms of nitrogen per hectare. If we wanted to use fresh urine, be able to apply the 85 kilograms of nitrogen, we would have to apply 15,000 kilograms of nitrogen per hectare. With our fertilizer technology now, we're able to bring this down to 600 kilograms per nitrogen, which is almost on par with mineral fertilizer or conventional fertilizer that you'd buy at the store. So that's very exciting. We've been able to achieve that grade in terms of the acceptance of the farmer, that they don't have to do multiple passes in order to apply the same amount of fertilizer. And you can also see from the yields that our fertilizer is also performing quite similarly. So one of our main goals within these projects was to produce pellets that fit with conventional farming equipment so that there was no barrier for the farmers' adaptation of the fertilizer. And through surveys, we see that the acceptance rate is really high, especially if it's in this pelletized form, that they don't need to change their equipment. So that works in a European context. In North America, they often use liquid fertilizer. They use these big spray booms. They have bigger farms than we do in Sweden. And so their liquid fertilizer can be more of the what they would be interested in. So it does depend where you are in the world in terms of what is the preferred final form of the fertilizer. And then you can see in the other picture the performance of the fertilizer. So this is growing barley in Sweden. And the mineral fertilizer compared to the urine fertilizer is a little bit darker green, growing very well, especially compared to the non-fertilized section. Most frequently asked questions that I get, the first one is always energy. How energy intensive is it? And it is energy intensive. To go from a liquid to a solid when it's 95% water, it definitely takes energy. So we're currently running at around 850 to 1,200 watt hours per liter. And we're looking at reducing that to 300 watt hours per liter by implementing more efficient heat recovery so that we can actually recirculate the heat that we're using at the moment. And right now, my primary energy source is solar energy. I have solar panels, and then during the winter, it's wind energy. And now we are also investigating the use of waste heat. So in Sweden, for example, we burn our garbage and there's waste heat generated from that. We can also think about a grocery store and all the cooling systems that they have. They generate an enormous amount of waste heat. So do all the ice rinks as well. So there's, and most of those forms of waste heat are not necessarily being reused. In terms of burning garbage, Sweden does use it as a heat, to heat the local district buildings. But even the heat that is coming back from that is still at an ideal temperature for us to use. So we see that we can be completely off-grid in the future. In terms of health and safety, I always get the question about pharmaceuticals. And the short answer is that it's a negligible risk for humans. There was a big study in Sweden that was looking at what happens if we have our waste going to a conventional wastewater treatment plant with the liquid effluent from that going into our surface waters, that is our drinking source, compared to using black water, which is the urine, feces, flush water, toilet paper, being used as a fertilizer. And they showed that it was a 10-fold higher risk of consumption of pharmaceuticals with the conventional system compared to using it as a fertilizer. So what it showed was that we would have to consume carrots or potatoes every single day for a minimum of 5,000 years to get one dose of the most resilient pharmaceutical. And it's up to 20,000 years for the other less resilient pharmaceuticals. Saying that, we know that we're having huge impact on the aquatic ecosystem from releasing the pharmaceuticals into our surface waters. And we don't want to repeat that mistake. And we now have the technology to actually better understand what impacts we are having at the microfauna level on the terrestrial environment. So research is going to assess how much of an impact we're having. We know that just applying fertilizer changes the microfauna. It stimulates the bacteria and the fungi that can live with those elements that are being applied. So then what happens with the pharmaceuticals? So long story short, negligible risk for humans, but still uncertain about the risk for the microfauna and then the rest of the food chain. So we're actually heavily invested in developing systems for removal through our partnership with SLU. So we have grants there and a PhD student that has been assessing different methods for removing the pharmaceuticals during our drying process. So if you're interested in that, we can definitely keep in touch, and you can follow us on our blog where we, on SLU blog, where we post different research developments that we have. And then in terms of pathogens and heavy metals, we meet the US EPA and WHO guidelines for reuse. because what we eat is so clean, what comes out of us is so clean, particularly with the heavy metals. And then there's only a few organisms that are transmitted via the urine that are directly a risk for us to ingest and be sick again. So it is a very clean fertilizer in that sense. In terms of next steps, we're investing now in optimizing the drying system and optimizing the pelletizing process to ensure that we have a good product that can be stored for a long time and maintain its quality. And we're also growing, so looking for investors, looking for partners, and increasing our urine collection, as that is always our bottleneck in terms of scaling up. And with that, I'd like to say thank you.
Great, thank you very much for that talk. There was already one reaction in the chat. I had the same when you mentioned at the very beginning that we are flashing away 1 loaf of bread every day per person. That's really it's a great picture to have this in mind, how rich our nutrient really is and what we are doing here by not recovering the nutrients.